Hello everyone, right, we're on to the next part of flight outside of the level regime. We're looking at climbing flight today, so this sort of stuff that's occurring here, probably not at quite such an extreme angle. We're looking at climbing flight. I realised looking back at some of my lectures, in a couple of them the resolution of the screen wasn't correct. It's still legible, hopefully in most cases, but I've set a post-it note that says check the resolution of my iPad display behind me. So let's have a look at climbing flight and what we're looking at. So let's draw our Earth plane. We're going to draw a line parallel to the Earth. I've managed to find out how to get a ruler on this screen, so it's now going to look like I can draw perfectly straight lines freehand, which would be pretty cool. Okay, so now this is then parallel to Earth. No, that's not a ruler. And we're looking at our aircraft climbing up at the angle gamma. I'm just going to choose a slightly different green as well, because I realised that green didn't look too great looking back at the video, so I've chosen a slightly different one now. Right. Again, these angles are going to be exaggerated for the purposes of what we're looking at, so let's draw our aircraft angle here. Let's try that again. Okay, so this is where our aircraft is going to be along. Let's draw our aircraft in. So this angle here is our climb angle, which has the symbol gamma. So that is the correct sign for the flight path angle. So we can leave this as gamma. We don't need it to be gamma bar. Let's draw our forces on. We've got, well, the aircraft motion is in this direction. So the aircraft lift is acting up here. Drag, I'm going to draw it as a big, actually no, let's just keep this small here. Let's say drag is in here. I've got the aircraft weight acting downwards, and I've got thrust pulling the aircraft forward. Okay, so as before, we're going to develop some relationships using the relationships that are normal to and parallel to the velocity to come up with force equilibrium to work out what's going on in a steady climb. Normal has 1L, normal to V infinity. So normal to V infinity, we've got the lift and we've got a component of the weight. So let's look at these weight components. We've got W cosine gamma, W sine gamma there. So the component that is normal, we've got W cosine gamma is equal to the lift. Let me just put my phone on silent. Okay, then we've got a single expression there, and we can determine the climb angle as a function of the lift and the weight. We're going to do the same thing now, looking at the forces parallel to the flight path. So looking at the forces that are parallel, we've got W sine gamma going backwards, we've got thrust going forwards, and we've also got drag. So we've got three things now. So we've got thrust minus drag is equal to W sine gamma. So we can then look at the relationship between these. We can say, okay, well, sine gamma is therefore equal to the thrust minus the drag divided by the weight. So that gives us the climb angle. Immediately we can say that a climb angle is going to be larger if we have more thrust than we actually require due to the drag, and it will be bigger if we have a lower weight aircraft. So this quantity in here, thrust minus drag, is our excess thrust. So thrust that's going to be here, we can consider this is our thrust available, and this is our thrust required. So that gives us the condition for the biggest climb angle immediately. And let's think about what's occurring in terms of vertical speed. So if we were, when we looked at the glide, we talked about the sink rate. So we talked about the sink rate was how fast the aircraft is approaching the deck. We can think about the climb rate is going to be the vertical velocity. Okay, let me put everything else in silent. I've got a bunch of messages coming in from incoming students. I'm starting to write a sentence without thinking, so we'll say similarly. Let's write that word properly. Similarly to the sink rate. So we can define climb rate so we can think about a means that we're going to determine that. So if we look at the velocity vectors that we've got v, which is the aircraft velocity going at the angle of the flight path. We've got two velocity components here. So we've got the horizontal one, which at the moment we're not concerned with. This one here is going to be our climb rate. So we can see immediately that v climb was just as it was for the glide rate, is going to be v climb is v multiplied by sine gamma. So for the sink rate it was sine gamma bar, now it's just sine gamma. So if we want to, we can now look at an expression for the climb rate. So it's taking sine gamma and multiplying it by v, and we already have an expression for sine gamma, which is up here. So we're just going to take this and multiply it by v, and it will give us an expression for the climb rate. So let's give these little simples. Let's say this is star 1, this is star 2. So putting the first into the second, we end up with the climb rate is equal to, well, we said it was v sine gamma, so that's v thrust minus drag divided by the weight. So let's rearrange this just slightly. We can talk about this in terms of the rate of increase of gravitational potential energy. We can say that W multiplied by V climb is equal to V T minus D, which is equal to VT minus VD. So we can look at the terms that we've got in here. So W multiplied by V climb, so that's the aircraft weight multiplied by the vertical speed. That's going to be the rate of increase of the vertical, or the gravitational potential energy. And so then we've got two components over here. This one is the thrust power. So a thrust multiplied by a velocity gives us a power. And the same one here. This is the power required. Okay, so we know this has units of power over here as well, but we can see here that the maximum climb rate is going to be given at the maximum excess power then. So we've just found those two conditions. We found that the maximum climb angle is at the maximum excess thrust. The maximum climb rate is found at the maximum excess power. So let's try and think about where these actually occur for a given aircraft. And again, we're going to break aircraft down into power engines and thrust engines. So remember, the maximum excess thrust is going to give us the largest value of the climb angle. So this is relatively easy to get for a thrust engine. So let's just remember how thrust engines work. So for a thrust engine, our thrust is constant with forward speed. So we can have a look at plotting thrust available and thrust required versus forward speed. Again, we'll probably, doesn't matter which sort of velocity we plot this against for the moment, because we're looking for a given altitude maybe. So this one up here, this is our thrust required. Remember, this just comes from the drag curve. It's going to be A multiplied by V squared plus B multiplied by V to the minus 2. So for a thrust engine, we've got constant thrust available. So the quantity that we're looking for excess thrust, thrust available minus thrust required. Call this delta T. So if we were to plot delta T on here, it would look like this. So we can see that this is maximum, if I'd drawn this properly, at the condition of minimum drag. So what have we just shown? We've shown that for a thrust engine, which is a pure turbojet or a low bypass ratio turbofan, the highest climb angle is found at the minimum drag speed. Okay, so for a turbojet or a low bypass ratio turbofan, the largest gamma occurs at VMD. Okay, and we know VMD It is the velocity associated with CLMD, which is B on A to the power of a quarter. Okay, so that's for a thrust engine. Think about how this occurs for a power engine. So remember, power engines are turboprops and high bypass ratio turbofans. So let's remember that the power is equal to thrust multiplied by velocity. So the thrust available for a power engine is equal to the power divided by the velocity, which gives the somewhat counterintuitive idea that a power engine at zero velocity is producing this idea of infinite thrust. Obviously it's not, but that's the assumption we're making with this model. So if we were to do the same exercise we just did a moment ago, we look at thrust, and then if we look at, got to remember how this plot looks like because I've drawn it out and I've done it on the website. I want to make sure I get this right. There we go. Okay. And we've got forward speed. We're going to plot our thrust curve, so our thrust required curve. And then we're going to plot our thrust available curve. Now, thrust available curve is going to start up really high and it's going to taper off. So let's have a look at what that looks like. So then what you'll see is that the difference between these two curves, depending how high this one goes, we'll often see that the delta maybe starts off and has a maximum very early and then tapers off very quickly, okay? How this occurs at the very beginning just depends on whether these two cross over or not. So our maximum occurs at a very low speed. So what's likely to happen if we try and approach this speed for a power engine? There's a good chance for a particular planform or an airframe you might have that our stall angle might be somewhere here anyway. So we might find that we've got this really great climb performance but could be limited by stall. So it's found at some speed that's quite a little bit less than VMD. And we'll say here, aircraft might be limited by stall prior, well not prior to achieving it, but might be limited by stall, meaning that that speed simply isn't achievable. Okay, so we've just done these two to look at the climb angle. So the largest climb angle is found at the largest thrust difference. So that's the difference between the available thrust and the required thrust. Okay. So we've done that for climb angle. Let's have a look at climb rate now. So this one is, because this is related to power, this is going to be easiest to look at for a power engine first. And you can probably already guess it's going to occur at the minimum power speed, but we'll do the plot anyway. So this is our power required curve. For a power engine, we would have constant power available. So the maximum value here of the difference is found at VMP, which we know is B on 3A. Okay. So for a thrust engine, we've got to look at what the thrust, or the power of a thrust engine. Power is going to be a function of the thrust multiplied by the velocity. So the power is linearly proportional to the velocity. So if we were to draw this plot, then we have, so we've got power, we've got forward speed. This is power required. For a power engine, thrust engine, our difference is just, our power available is just a straight line. So the maximum value here is going to be at some intermediate value up here somewhere. So but it will be at some speed that is greater than the minimum power speed. So that's how we determine the two types of maximum climb rates. So we can just summarize those briefly. Okay, so we're going to remember that the climb angle is proportional to the difference in thrust. So this is easiest to get for a thrust engine, and this occurs at VMP. For a power engine, we are remembering that we effectively have really high power at low speed, so the difference is going to be at some speed that's quite a bit less than VMD. And I've done the same thing on that last one, which was very annoying. Let's cross it out. These are our minimum drag speeds. Okay, then the maximum climb rates. So remember, this is proportional to the maximum excess power. So this is going to be easiest to determine for a power engine and occurs at VMP. And then for a thrust engine, remember our power is linearly proportional to speed. So this is going to occur at some velocity that is higher than VMP. So if I give you a question with these, and we're going to go through some examples in the Wednesday review session. If you need to determine this one or this one, those are easy, because then we know that those velocities of VMD is equal to B on A to the quarter. VMP is equal to B on 3A to the quarter. If you have to determine these, but do it numerically. There probably is some means you can determine the maximum difference between those two. It might not be too difficult, might be a bit of involved calculus. I haven't done that. We can go through and have a look maybe, but it's just going to be easiest to do it numerically. So if we look at the website, and I'm going to have to mess around with my screens, which is great. There we go. Okay, so these graphs here are all the ones that I've been sort of drawing by hand. Now try and reproduce these on your own if you can. I want you to go through it so you can see where these values are. Now the parameters of this aircraft here are given. Okay, so we've got this turbojet aircraft here, and we can produce these. And then for a turboprop aircraft, I've produced these two graphs here, and I'll try and see if you can produce them on your own. And try and match the data that's available here. If you cannot, you can always look at the source. You can look at the source of this page. I think I've hidden the code here. Yeah, I've hidden the code. But you can always download the source if you want to and have a look at it. But I promise you, you'll do better if you try and do it on your own. So that's climbing done. That was quite a quick lecture. We're going to move on with looking at range next. And looking at range, we're required to have an appreciation of climb. So we're going to go through some numerical examples of both of these, both the glide and climb, in Wednesday's review session, and I look forward to seeing you guys.